Hey everyone, thank you for joining us for our next AI Apps and Agent Dev Days session. Before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenters to answer. Our session is being recorded. It will be available to view on demand right here on the Reactor channel. With that, I'll turn it over to our speakers for today. Thank you so much for joining us.
All right, hello everyone. So my name is Anton Slutsky. I'm a part of the NVIDIA Solution Architecture team. And I'm joined today with my colleague, Diego Casari from Microsoft, who is a part of the Global Black Belt organization there. And we're talking today about the AI Research Assistant Blueprint in conjunction with AKS, and kind of diving into a little bit of the agenda for today. So what I'm hoping to present to everyone today is a quick overview of NVIDIA AI Enterprise Suite that is currently available on Azure. That will be followed by my colleague Diego discussing AKS and its capabilities on Azure. And then we'll conclude with a hands-on demo around the AIQ, which is our deep research agent that we will be deploying again on AKS using our blueprint artifacts available through the NVIDIA portal. So let's start with a quick overview. So just a quick overview. So Microsoft and NVIDIA have a very long-standing collaboration that spans over 30 years working together. This collaboration started as part of the R&D efforts, working together on libraries and software that Microsoft uses for its kind of like first-party products that use accelerated GPU hardware available from NVIDIA. And this collaboration is still going on today quite actively. And some of the examples of the results of that collaboration could be seen in products such as Microsoft Teams, Microsoft Bing, kind of like another products that use accelerated hardware, NVIDIA accelerated hardware for its internal applications and user-facing applications. From another angle, NVIDIA works with Microsoft towards offering services to customers to make them more successful in the usage of NVIDIA hardware and tools. As well as the software available on the Azure platform. So on the software side, on the hardware side, we are, as you can see kind of on the slide, there are popular products such as A100 and H100 GPUs that are available on Azure Cloud. These are the ones that we'll be using today for the demo. On the kind of newer offerings coming from NVIDIA, we have the NVIDIA Blackwell chip that is kind of like one of the most recent entrants into the Azure cloud space, as well as the very recent early access one, which is the RTX Pro Server GPU. That's again available in as early access to on Azure cloud. In addition to hardware, NVIDIA also creates software, and that software is available on Azure as the overall offering being termed as NVIDIA Enterprise. NVIDIA Enterprise is the overall term that describes the software that's available on in general from NVIDIA towards the enterprise consumer. And as mentioned, the enterprise consumer can get that suite of software and purchase the license for the software through the Azure Marketplace and build their own use cases, take advantage of all the tooling that's coming from NVIDIA that helps integrate with multiple hardware offerings as well. So kind of looking into some of the important innovations. I mean, the collaboration has been going on for some time. Some of the important innovations that are coming out of NVIDIA, the overall name for AI models that NVIDIA publishes is the Nemotron family of the models. These are open source models. These are available as I mentioned, open source, open weights. You can find them on Hugging Face, as well as Azure Foundry. And in addition to the models themselves, what NVIDIA does, it actually also open source the data sets that are used for model training, that were used to train the particular models, as well as kind of cookbooks and libraries and pipelines available through GitHub that were used to build the Nemotron models. This is the purpose of this is to kind of enable the community to innovate faster and iterate faster using our essentially work that was done by NVIDIA internally to develop these newer models. So you can use these models to integrate you can use these cookbooks and tools to integrate these models into your use cases and use them to kind of extend as you need to see fit to produce newer models and your own implementations. So really what we're trying to accomplish, what NVIDIA is trying to accomplish with kind of this openness is the find an overlap between intelligence, efficientness, and openness. So you will find a lot of our models in the public domain, on the public leaderboards, in kind of leading spots. And what we're trying to do is to make these models available to ensure that they address the various use cases that are the community is coming up with, and that are emerging in the kind of like as the community progresses through the use cases that are becoming more prevalent in the industry. Some of the latest breakthroughs and advancements that are coming out of NVIDIA. As I mentioned, Nemotron is the family name for NVIDIA AI models. The latest Nemotron model is the Nemotron 3 model, and the very latest one that was published literally a couple of weeks ago on Azure Foundry, Microsoft Foundry, is the Nemotron 3 Nano that is, as mentioned, currently available in the Foundry. And what we're seeing a lot of performance improvements, from adoption of the mixture of expert architectures. As many people know, there's a kind of several popular architectures that are out there today that are implemented by AI models. The most maybe well-known one is the transformer architecture, and then there's a Mamba architecture that's also a competitor in the space. So what we've done as far as kind of our innovation, our breakthrough, is we're using a hybrid model where our models use kind of combination of the transformer architecture and the Mamba architecture, and that has resulted in significant performance gains that you can see on public leaderboards out there. We're very proud of and excited about. From the point of view of the reinforcement, we're also using reinforcement learning techniques to kind of steer models towards improvements in the reasoning capabilities, and to kind of improve and enhance the reinforcement learning processes. We're offering a tool called RLGym, which is an open source library that is helping developers produce models faster and improve performance gains. And these gains are essentially measured in terms of how well a model follows instructions, as well as how well the overall model correctness could be measured. And then lastly, with these optimizations in the modern kind of agentic environment, there's a significant push towards model with larger context windows. And again, our tooling allows, hybrid Monson allows our models to have quite large context windows, which makes them more suitable for modern agentic applications. Another way to make it easier for the industry to adopt models is we're packaging them as containers. That is done so that developers can run models easily in production environment with as little overhead as possible. And the name of these containers are referred to as NIM. NIM stands for NVIDIA Inference Microservice. The goal of this containers is to essentially enable developers to run these easily on any containerization platform out there. And of course, in our example here, this can be easily run on Microsoft Azure. And in fact, in this session, we will show an example of running a NIM container in Microsoft Azure using AKS service. Some of the advantages of using NIMs, why NIMs matter, why people might want to look into NIMs, is as I mentioned, these are platform agnostic containers. So any containerization platform, any platform that supports containerization could take advantage of NIMs. The NIMs implement industry standard APIs. So, for example, NIMs implement models implemented as NIMs offer OpenAI API implementations, and that makes it possible to use kind of standard OpenAI SDKs to communicate with these models and plug them into whatever orchestration infrastructure you prefer. Also, NIMs offer support for custom models, so you're not limited to only models that come from NVIDIA. It's also possible to use custom models within NIM containers. These could be your internal models, or it could be fine-tuned models, or models with LoRa adapters could be inserted and used within the NIM containers, taking advantage of all the NIM optimizations. And in addition to NVIDIA models, we have a set of NIMs that implement expose domain-specific model from public domain, so also packaged in NIMs. So these are models that are specific to a particular domain in the open source community that may be particular to a particular application or particular vertical. Again, they're implemented as NIM and take advantage of the optimizations that NIM provide. Here is a quick example of how easy it is to use, experiment and use these models and switch between them. So as you can see, it's a very, very quick code example. This example is using, as you can see, the OpenAI SDK. This SDK, I'm sure, is very familiar to most users, and you can see here, kind of highlighted in green, is how easy it is to switch between their different models. In this case, we're switching between Llama 3.1 405B to DeepSeek R1. So it's literally half a line code change, and you can experiment with models using standard SDKs. So just to drive a little bit the point regarding kind of development overhead and the ease of use of NIMs versus other approaches. Of course, it's possible to train your own models. You can use those with any inference frameworks, implement your own frameworks or APIs. You would have to kind of run optimization for a particular use case, run optimization for particular hardware, which is definitely possible. But in practice, we're seeing that this process may take anywhere from several days to weeks or longer, depending on the application. By using NIMs, developers can speed up quite significantly this process from sometimes many days to a few minutes, sparing themselves from having to do quite a lot of work that's already been done. The work that's already been done on the NIMs is the performance testing and performance optimizations, GPU optimizations, making sure everything works on a particular GPU hardware, of course, coming from NVIDIA, as well as the packaging overall as a container, as containers, making it easy to deploy within the containerization environment. Essentially, all the developers need to do is just to run the NIM container in their environment and pick and choose their model name or provide their own, and they're ready to go in just a few clicks. So as I said, we have Nemotron models as well as open source models, but there's also other models that are available as NIMs. So, for example, speech models, computer vision models that handle, computer video and image input, as well as a number of industry-specific models. For example, biology models that are used in many organizations for pharmaceutical drug discovery, protein folding, and kind of things of that nature there. And as I mentioned, all of these models, many of these domain-specific models are available as NIM, which makes them, take advantage of some of the efficiencies that we were able to implement in the NIM containers. And I'm definitely encouraging everyone to if you are in a particular vertical, please take a look and try to find something that might suit you. So overall, as I mentioned, NVIDIA Enterprise is available on Azure Marketplace. And NVIDIA contains NIMs, which are part of the NVIDIA Enterprise suite. But on the other hand, we also have more software tools available other than NIMs. For example, one framework is the NEMO framework. That's available again as part of NVIDIA Enterprise. And the goal of NEMO framework is to help customize your model, help with the model evaluation, as well as guardrailing for production use. So we're creating kind of like what we call a continuous data flywheel, as we call it, which is structured around application for continuous monitoring, model optimization, and the kind of model deployment lifecycle. So that creates like a lifecycle loop that could be used to easily manage your models in a realistic setting. Also, because modern agentic applications often use multiple models or combinational models and libraries, NVIDIA publishes what we call the blueprints. And what the blueprints is a starter code for many use cases that developers can quickly get from GitHub repository maintained by NVIDIA, and use that code as either directly to production if that fits your particular use case, or as inspiration for further development and further work, where we definitely encourage people to modify those and to their needs. Some of the examples of the blueprints that are out there, some of them could be the customer service agents. So we have blueprints for the basic customer service example, as well as the research assistant agent, which is the demo we'll be doing today. Diving quickly deeper into the blueprint concept, what the blueprint consists of are the kind of reference application configs, some sample data in many cases, some reference code implementation, architecture documentation, some of the customization tooling, and then orchestration as well, orchestration tooling. So blueprints have all these major components that developers might kind of need and use to get started for a particular use case. And do that quickly and efficiently with as little kind of development overhead as possible. And all developers have to do is kind of modify the blueprint and use it for the use cases as they see fit. Some examples of the blueprints, as I mentioned, there's a large repository out there on build.nvidia.com, but just to name a few, React is a popular one, and we'll be using React blueprint as part of our larger blueprint today. BioNemo is a popular use case for biological applications, and another popular one is the video search and summarization, which again handles kind of some of the video processing and summarization of the video input. So as I mentioned, lots of different options out there. Please go to build.nvidia.com and try for yourself and explore those blueprints there. So kind of pivoting a little bit to the demo we're about to do, kind of give everyone a little bit of a flavor of what a deep researcher is. So we'll be deploying this what we call AIQ Blueprint. The blueprint is essentially builds this researcher agent And so this research agent has several kind of like steps and that flow that it follows. We'll be creating the agent, This agent will analyze the data set which we will provide, create kind of like a research plan towards the particular query from the user given a particular data set, and eventually create a structured report based on the data that the user would have supplied. And we'll obviously have an example there. The agent workflow will start from user query, then it'll go in the planning stage that would develop kind of like a research strategy, and then search different sources, and then synthesize a report with citations and present that to the users again, which we will show in a little bit. So this takes this is one step further from the kind of like common RAG approach, where you just kind of query the data and generate the response to the user. Kind of in contrast, the agent that we're about to demo conducts an involved process before it returns anything to the user, with a lot of reasoning and so on being used there. So here is the overall architecture of the blueprint that we're going to demo today. All the items showed in green, that you can see in green boxes, are the Nemotron AI models published by NVIDIA. As I mentioned, kind of like you can see the lower left box showing the RAG section. So RAG is a separate blueprint that is part of a larger blueprint, which is kind of a subsection of the larger reasoning deep researcher agent that we're showing there. So the RAG blueprint is used to kind of ingest data, retrieve data based on query, and we also have a web search functionality that in those cases where the main orchestration agents decide that it needs additional information from outside the context that provided by the user data set, we're able to go to the web and query the web and produce and combine that with the data set itself. So the most central piece, as I mentioned, outside of the RAG and a kind of like central place, is the reasoning Llama Nemotron Super 49B model, which is kind of the main orchestrator for the use case. It creates a research plan, analyzes the user query, generates reasoning steps, and then synthesizes the final answer. As you can see, though, the report itself is actually produced by a separate model, in our case, Llama 3.3, which uses kind of like formats and finalizes the report given the results of the Nemotron Super. So that's as far as the overview. I'm going to quickly now jump to the final interface that we're hoping to see in the end result of this demo. So this is what essentially what the user interface of the actual agent would look like. So here you can see the web user interface that we can start, begin research. We can choose a collection. In this case, I will pick biomedical collection data set, which is quite large, it's 167 megabytes. And this is kind of a report topic and as well as some instructions of what test user might suggest for the research assistants to research. And so we would select the sources, and then essentially validate everything, and then start generation. And this will create the research plan, right? So this is kind of giving you all the reason. This is live running against a particular agent right now. And so once that's basically, this might take some time. So basically, I'm not going to, here we go. So if we click execute plan, this might take a few dozen minutes. So we're not going to wait as long. I'm going to kick it off, but I'm going to kind of like see what it does. It tries to execute the plan. I'm just going to quickly drop into the result of it. So this is the result of this operation. It has the agent had conducted these particular steps from RAG answers, relevant checker, so when some web answers, some summarization, running summary, and so on, and then produce this good-looking, nice-looking report that is formatted with, I'm assuming, some biological output there. And so this is what we're trying to get to. And now I'd like to transfer control, Isabella, if you could, to my colleague Diego, who will now hopefully take take the camera and maybe walk everyone through the actual use case.
All right, sounds good. Thank you, Anton, for this. We're just moving over here to my screen. There we go. Thanks, everybody. I'm Diego Casari from the Migrate and Modernize Global Black Belt with Microsoft. I'm coming today or tonight at this hour here, 7:23 p.m. Mountain Time, directly from Calgary, Canada. I saw a lot of cool comments here from a lot of people from everywhere: Mexico, Texas, Georgia, California, of course, Australia. We have folks in Colorado as well. So thanks for joining us. What we're going to try to do here today is to give you some ideas of how you can actually deploy and use what Anton went through here. To be clear, this is live. This is not an actual cooking show. So what you're seeing is live on a cluster right now in Azure. We did see that NIM, when deployed, in this case here, will have two blueprints. One is a AIQ, essentially, when Anton went through the report here, so as we were selecting a collection, a biometric data set, and then he ran over this with the PDFs and all that. That's a part of the solution. The second part of the solution here, and I'll show you real quick, is RAG. And this is running in the background as well. That is, again, both of them play a role here. As you ingest new data, or PDFs in this case, for our example, they will land here. And you have full access to both of them. So at the end, from a data scientist perspective or an end user, this is what we want. We want to go back to the report that we have. We can change the report as much as we want. And then once we're satisfied, we can download it as Markdown as PDF, right? We can also chat with that interface as well. So as we're asking questions here, well, things are happening in the background. And I'll show you and I'll walk you through how do we get to this view now. So what's happening here is that we have telemetry from this cluster. I've instrumented the cluster, and NIMs, all of the inference microservices that we have from NVIDIA, they do provide telemetry. That telemetry is then collected, and it is being displayed here in Grafana. This is Azure Managed Grafana. And the cool thing about this is that we can now actually have a look at how the LLM behaves. So from the time of the first token, which is the first graph that I'm showing here at 375 milliseconds, to a throughput of number of tokens per second, successful requests, finished requests, moving on into latency, and then have heat maps from that, we have interesting telemetry that we can get. And I'll come back to this, but I want to pick your brain, because this is where, at the end of the day, we're also providing. Of course, we have the solution, but from a day two operations perspective, once we have this deployed and running, well, how do we manage? Is there any telemetry here? And I'm showing you some of them that we can use to make sure that our solution actually works. This is all based on Kubernetes. So again, this is doing, everything I'm showing you here is live on top of AKS. I will expand real quick here so you can have an idea of what we have. We do have access to the vector database that lives in cluster. And I also have GPU-based telemetry. So I'll show that real quick so you can kind of see, but I'll come back to that. But this would allow us to actually fine-tune this system and make sure there is no choking points, whether that's GPU, maybe it's network, maybe it's more RAM that we need. What can we do about it in case we get there? So let me walk you through the workshop that we have with the time we have, and then we're going to circle back to this here. Now, here is our solution. We'll share this link with everybody so you can see it. So don't worry too much about copying that out. It's on GitHub, so you can just clone it. The whole solution here, I'm just going to make this a little bit smaller. There we go. Can be deployed through Cloud Shell. In fact, I will show you how you can do it. Now, if you don't want to do this through Cloud Shell, that's fine. Everything that I have here, from the environment variables to some of the other commands, were suited for Bash. So as long as you have Bash, you're good to go. You can do this on Linux or Mac. It doesn't really matter. You can get this done. I want to show you the diagram, and Anton already went through this, where we have RAG, and I show you that here with the RAG blueprint. And then, of course, we also have the AIQ, which really is that interface we saw with the researcher. You have three options here, and I will go back to them in a second. But in a high level, we can either have it running on AI Foundry in Azure, which is what we have on this diagram. You can also have it pointing directly to NVIDIA. So you get an API key from NVIDIA, and you're off to the races. This will fit different scenarios, and I'll walk you through them once we cross that bridge. The last scenario, which is the one I'm showing you today, which is what this demo is all about, is actually to have the Nemotron Super 49B inside of the AKS cluster, right? So everything is on the cluster at this point. So let's go through that. In a nutshell here, I'll walk you through the core areas that I think are important if you're following along with this, or if you want to try later on. Of course, the number one is, what skill do I use? Well, there are a few skills that you can actually use, and they will vary depending on your subscription or region, and if they're available or not. This will work just fine with any A100 GPU or H100. For this demo right now, I'm actually using a standard NC series, and on that series, I am actually using the 80 ADIS H100 version 5. So this will work. Again, you can try with other options here, and it should work as well. We're going to check a few tools here. I left them in there too. Of course, you do need Azure CLI to deploy this. kubectl, Helm, everything is done through Bash. You do need Git, and I'll tell you why. I have a lot of manifests already on this repo here. If you don't want to use that, we're just going to git clone this, and it'll make your life a lot easier. If you feel like that's not your vibe and you just want to do a kubectl apply versus the raw file in GitHub, hey, that works too. You just point out to the manifest file and you're off to the races. You do need an NVIDIA API key, which is this one right here, free. You can just click on the link, it will take you there. And then Tavili is also needed. Quick stop here on Tavili. Tavili is used, and it was used when we were actually doing the research. So I'll click real quick here on another screen, and I'll bring this so you can see why. This will, so just for the medical data set that we had, right here, you see the web search. What this will do is it will enhance the generation of the answer back, or if it doesn't know based on the RAG, the files that it has already, it will reach out and it will fetch that information. That's why we need that. So Tavili, again, it's a free key that you can get, but we do need that later on. In terms of a footprint, what exactly are we talking about for what I'm showing you right now? Again, the other portions here, let's say if we're just doing an API call through build.nvidia.com, well, you really don't need all of the H100s in that case. You can probably just get by with having the A100s, and that's fine. But if you want to have the NIM LLM and everything that I'm showing you in cluster, then it follows that you do need 4 nodes with H100s. And then I'm separating a system node pool with 2 of the D32S V5. Moving along here, I'll show you how you can get to Cloud Shell if this is your first time doing that. So I'll skip this real quick, and then I'll come back in a second. But what we're going to do, we're going to go to Cloud Shell now, and I'm going to clone this repo and at least show you what's behind there. And then we'll come back to this view here in a second. So I'm just going to get out of full screen here real quick. I'm going to go to this RAG demo here. Now, this is running in Azure. So if this is the first time you're doing that, I'll show you how. This is my AKS cluster, the one we're doing for this demo. You can see that I have 2 node pools. At this point, we're kind of not worried about the type of CNI being used or anything like that. But if you are curious, this is just doing Azure CNI overlay mode. Up here in the bar, we have an icon that says Cloud Shell. Again, if you want to do this in your own terminal, go for it. This will work just fine. In Cloud Shell now, which might look exactly like what I have here, I really don't have any files in there. So it's pretty much blank at this point. So the first thing I want to do is to clone. Cloud Shell does have all of the tools that I mentioned, so you wouldn't have to install anything. We're doing a git clone to github.com/nvidia/nim-deploy.git. Let's see if I can make this a little bit larger. There we go. And then we're going to cd into NIM deploy cloud service providers, Azure, workshops, and then AIQ Blueprint. This is also, this instruction here is as is in the workshop, so you can just copy and paste from there. What you see here are a few things. I actually left a bash script in it in case you just want to run it. It will deploy everything for you. Right now, I actually want you to understand what we're doing instead of just automating the process. It is a little directory, and that's really the one directory that I wanted to pay attention, which is called manifest. Everything that we need is there. So you could also just do a kubectl apply and then point to this directly if you don't want to clone it. Right now, once we have that, we're looking at a couple of things. I actually do have the cluster pre-deployed. So I'm going to go back here and I'll show you. We're just going to follow along the instructions for a second. I'll show you what's going to happen here. Once we set everything up, we are pulling the Nemotron Super 49B to the cluster. So that's important. And with this, and for you to have all of these cool graphs, and it looks like you're in an episode of Mr. Robot with Managed Grafana, I am setting up a Grafana instance and then also an Azure Monitor workspace. And then we're coupling those together. Once the cluster is deployed, everything is pre-wired. If you already have one, you don't have to set up one from scratch. You can just point to that one and it works just fine. So once we move into this and everything is deployed, so now you have your cluster and you have Grafana, right? Everything is wired together. I'll also make a couple of calls here. One, the dashboard you saw, I'm calling that consolidated NIM dashboard, is also available for free in this repo. So you can just import that. Second, once that's done, we're going to capture here the credentials for the cluster. They'll do it live so you can see it. And then we're going to create a node pool. An important point here is that normally you would go with AKS, and AKS will actually give you a way to, once you deploy a node pool, especially GPU with NVIDIA, that really you don't have to set up any drivers. So we install that for you. In this particular case, I'm showing you end-to-end everything in case for some reason your SKU doesn't have that support. So you can learn how to do it, and honestly, it's just going to get easier from here. On that node pool, once we install it, as you can see here, right, we have a dash GPU driver equal to none. And once that's done, the GPUs won't have the drivers. They will be up and running. The GPU operator is not installed, but the node pool is there actually at this point. We're going to follow through with the installation of the GPU operator. And then in here too, and I have notes here in the workshop, what exactly are we doing? Because I'm giving you a value file, and I'm also at the same time giving you some flags. The flags are, we're enabling of course, we do need the driver for that. And then we need something called DCGM. DCGM will allow us to have all of the cool metrics we have seen here. Everything you see from a hardware perspective, or a GPU perspective, DCGM is the one that is bringing us that. So we're going to install that, and we're also going to install a few other components. The one thing we won't install, if you have done this before, is the service monitor. A service monitor in this case here is a Prometheus service monitor that will allow Prometheus to actually harvest some of the telemetry from a pod or a service. So if you have a bunch of pod behind the service, and then with that, we can send that telemetry and craft it out on Grafana, right? I don't want that because I'm also customizing a little bit, and I'll show you why in a bit. Takes about six to 5 minutes for everything to be up and running, as we see here, but it would have the daemon set, the operator, the feature discovery, everything is in place. So before we continue here, I'm going to go back and show you that live, right? So let's go in here. And again, you would be deploying everything from this directory. I don't need to be in this direction right now because things are deployed, but I'll circle back on that if I have to. So the first thing I honestly do, especially because I'm doing this in Cloud Shell and I don't actually have all my shortcuts, I'm going to do this. Alias is, K is equal to kubectl, because honestly, if you're like me and you spend your entire day in Bash doing kubectl commands, you do not want to type kubectl 10,000 times. So we're typing K. But right now, I really don't have anything. So this is probably like what you have. You've deployed the cluster, but you need to get the credentials for the cluster. With that, we're going to do an AZ AKS. I will list my clusters here so you can see it, and then I'll show you how to get a specific kube config for a cluster. So I do have a few clusters in here. The one we're interested in is called reg demo. So AZ AKS get credentials. And then the name is this one right here, which is called reg demo. And then your group, or my group in this case, follows with that name. All right. So now let's go back to my kubectl get node command and see. Boom, it's there. So we can see that we have the GPU node pool here with 1, 2, 3, 4. That's how I configured. GPUs, nothing here is right now is auto-scaling, more on that later. And then 2 of your system node pools. And then if I do a get namespaces, we can see we have a few namespaces. They will make sense here in a second. The one that I just showed you is the GPU operator. So let's just do a quick look at what's in there. Get pod, and the namespace is GPU operator. And then we see everything is running. And then some of there were some jobs and things that need to be completed. They are done too. Great. Everything is ready to go. All right. Now, if we go back here, the next thing is to install the RAG blueprint. The RAG blueprint, once installed, will give you this view right here. That's the front end to the RAG blueprint, right? Now, again, there's a few things that I did here, and it's all in this repo. Just to simplify a little bit, I have a rag-values file. And the only one thing I want to call out, because if you do go back and look into this, you're like, why would he send tolerations to GPU no schedule? Well, chances are if you're doing this in production, you're testing this, you really want to have this toleration in place for the workloads. And of course, the node pools need to be tainted. The reason for that is this. With this, we ensure that workloads that are specific, tailored for GPUs, are scheduled on this node. Even though they might be just using CPU, I want to try to minimize that. Right? We don't want it to consume memory or anything like that. Right? The reason I have that is for this. So we are guaranteed to only have GPU-related workload on that node. Of course, there might be some other things that could potentially live in there, but I left that toleration. You can remove it if you want. It won't hurt you right now for the demo here, but I left because I think it's a best practice that we work with customers all the time. Now, after that's done, a new namespace is now online called RAG. This can take about 20 minutes. It's kind of a reason why I'm not doing everything here live. It's because we would be just here waiting for everything to come online. But once that's done, we can actually take a quick look and see what's in it. So let's do that. So if we go back here to the terminal, if I do a kubectl get pods-name and then rag, here we go. We have a lot of stuff happening here. The core couple of things that I want to show you, of course, we do have the front end, and that's the one we have web access there. I do have the Milvus, which is a vector database that's in cluster, which we also have telemetry that we can show later. There are some other things here like Redis as well. And of course, you have the re-ranker and embedder in here. So you can see them down here. The next step after that is done, and we confirm that everything is working, is a crossroad. We're actually now at one of those choose your own adventure type of scenarios. We have 3 scenarios here. One, I mentioned in the beginning, it's option A. You just use Azure AI Foundry. It is a managed service, get up in minutes. You essentially configure everything there, choose a model from a catalog, and you have an API, and you call it a day. That's it, production ready. The option B is using the NVIDIA Build API, which is a hosted API, which I think is amazing because you can just essentially have this up and running in seconds, good for prototyping, testing, trying different models. And then option C, which is what I'm showing you right now, self-hosted on AKS, takes more time, as you can see it, but also you have full control end-to-end across the board here. In fact, you can make this cluster private if you want and just have it fenced out. So that's the option we're doing here today. Each one of these, if you click on them, they'll expand. You have instructions. Again, let's take a quick look here. What exactly we're talking about with the Nemotron Super 49B locally on AKS. I do have, again, a file, values file for this with some configuration inside. And once you apply that, we can then have this model, the Nemotron 49B, running on a node. It doesn't need 2 GPUs. All of that is set up on that file. Next for us is we will expose a front end for AIQ, which is this right here. And then we need to load the collections. So the folks that actually wrote this originally here, they made it very easy. So there is a file. Once you run it, it will have the collections in place for us with all the PDFs, so the biometric, the biomedical, and the financial research are in place. Once you do that and those data sets are loaded, you're good to go, right? And then you can test. Now you could go down here, stop right there. And that's the demo up to this point, right? Where we are showing you how this can be done, and we're showing you, how to do analysis. Again, that is the core idea here. As an organization, this is what I'm providing. Stepping further, let's look at the monitoring and observability at this point. Now, a couple of things that we have in here that I think it's interesting. I only have actually a subset of the whole thing. You can do a lot more. I'm showing you some of the things that can be done, but we can actually have a lot more telemetry. I'll show a couple of things for you here. The DC gem exporter is the one that will have hardware-related information. And then we do have ways to gather more telemetry, and I'll show you how. Oh, there's one interesting thing here. We're not going to have time to show on this demo, but we do have Phoenix for distributed tracing, and it's available. So if this is something you're interested, you want to see how it works, you can open it up, just port forward that, and then with it, you can do things like latency breakdown and token usage and whatnot. So I think it's quite interesting. So the whole solution is actually fully instrumented. From a service monitor perspective, and I'll show you that here. I'll go back and open this up. We have a few things. Again, I told you that some of these components will have telemetry, right? And I'll show you that here in a second how that works. So if we go back into the terminal here, to bash, let's, for instance, take a look at how the NIM LLM, what kind of telemetry do we get out of it. So if I do a kget po-n error, I can see that the NIM LLM is right here, right? So I'm going to copy this out. And then normally, if you were doing this for the first time and you don't actually know what port number or endpoint should I be querying here, you could do this. You could just try to describe it. And really, we're looking for a couple of areas here. This right here is where we want to go. This will tell us that right now on port 8000, we have telemetry. So a cool little trick that I actually learned is that inside of Cloud Shell, you can actually do port forwarding. So if I port forward this pod and 8000, I can then, I'm just going to have to make this tiny a little bit smaller so I can actually see it. There you go. There is a web preview button that I can hear. There's a web preview button. And you plug in the port number, and then you open and browse. Now you would see this. I do know that this is actually living in /v1 matrix. And boom, we have it. So what do we have here? These are all the telemetries that are available. Again, not even one of them are being plotted right now on that dashboard in Grafana, but you can see them in here. So how would you go about actually plotting this or making a graph out of this if this is the first time you do it? Well, one way you can do it, let's do this together here. I'm going to move in a second window here, hopefully side by side. Let's pick, so I see here, each we request latency in seconds, right? So you would go here in Grafana and actually see it down there already, but you would plug that in, and they will tell you every one of the metrics that start with that name. Of course, you can use regular expression. You can be quite creative here. This, by the way, it's under in Grafana. You just go to the home icon here, drill down, metrics, and then you would plug that metric in here, right? You can see that I have a lot of other stuff for other parts of my cluster. But this is how you would do it. Now, you 100% at this point in time, if I just have that in there, nothing is actually taking this telemetry and sending anywhere. And that's where the service monitors or pod monitors will come into play. Now, real quick on this, if we go back to this repo and we go to the manifest, I do have a single file called service monitors. But the one that I just showed you, that's how it looks like. The modification here, if you've done this before, is that the API version is AZ monitoring instead of just monitoring.coreos. And then you can see that I'm actually going and scraping this every 30 seconds. And the endpoint is /v1/metrics. So every 30 seconds, we have that flowing back, and then I can now display that on Grafana as a graph. The other cool thing that I want to show you, which is also part of this repo, we have a way to actually do some load testing. The team at NVIDIA wrote a bash script called reg sweep hpa.sh. Kind of turn that into a job, so you can just run that as a job. And then at the end, you would get a little matrix that GenAI-perf, that's the utility that runs this, will give you like things like time to the first token or request throughput per second and things like that will show up. So this is quite interesting as well. And it is a job and you can just run it. Keep that in the back of your mind because this will do a bit of a stress testing. But why would you want to do that? And that's going to be a little bit of the next stage here. Again, I left a handful of telemetry for you here. You can see them with some description. But of course, they're not everything. I mean, I just showed you that the NIM itself had a lot more than what I'm showing you there. But we do have things from energy consumption, frequency, cache hit rate in the actual data store that is local, Milvus, the vector database. And then from DCGM, we have a ton of metrics here as well, right? So those are there. So let me show you here now live in real time, how they work. You can see the GPU clock frequency, Tensor Core capabilities as well, bandwidth. And then a couple of interesting things in here. If you were to have any issues, hardware-wise, they would populate here too. We don't have anything. Demo gods have been really grateful with me this week, so everything seems to be working just fine. But if you do encounter anything, that's where you would see it, and you can then trigger an alert after that if you want to. A little bit more of what DCGM can actually do, which is a very, very complete toolkit, PCIe bandwidth and whatnot. And then the last thing here is that from a NIM perspective, I can also look at memory and GPU utilization from a specific NIM. So you can see like I have ranks and re-ranks and all of that, and I can identify all of the stuff you're seeing here are available. And again, a subset of what you can actually do. I want to call out your attention for a couple of things, because I did mention that you can, so if you go back here, that you can actually do a load testing on this, right? And a load test on a system like this one would give you a few things. One, of course, you can graph it out, and I guess you can at least validate that everything works at once if you don't want to go in the other path, which would be this one, where I'm validating, metric by metric. Or how about we actually look at what Kubernetes can give us, and then we try to enable horizontal auto-scaling of the LLM in cluster. And that's a lot more interesting, actually. So if we do that, this is probably a very, very good documentation to have at hand, and we'll share the link with you as well. What this is doing, and I'll go back here to the top, is how do you actually enable horizontal auto-scaling for enterprise RAG in Kubernetes? Meaning, if we were simulating a load test, but if we actually have users using this to a point where we do have choke points in the system, well, how do we scale? Well, normally in Kubernetes, one of the ways I guess you would scale here is just using a horizontal pod autoscaler. That could be CPU-based, it could be memory-based, it could be a number of things. Here, what we can do, because we have telemetry, we have two approaches. One, which is what the blog post here describes, is to use the Prometheus adapter. So with the Prometheus adapter, I can actually look at this telemetry and then scale out. Let's say I have a lot of traffic, and then potentially, I do need another virtual machine that NIM can live on. Well, that's the way to do it. You just wire everything up. Once you have an exception, Azure will capture that, and then we're going to have the autoscaler from a node pool perspective kicking in, having another virtual machine. Once everything is up and running, you're off to the races again. The second option is to use KEDA, which is the Kubernetes event-driven autoscaler. Now, AKS actually has a flag that you can turn on and then have KEDA installed on the cluster. So it's a fairly simple solution. With that, what you do is you wire this telemetry coming from the cluster with KEDA, and then you take the appropriate measures, like, hey, what is the scaled object that I'm looking at here, and what do you want me to do after that, right? And they will force it so that the same mechanism or the ideas of a chain reaction here would occur. So two different components that could give you the same results here with your autoscaling. I do think that this is actually a very, very interesting segue, and I think if you're looking into this, this should probably be your next step once you do, the rest of the things that we described here today. And then one last call here. You can also do a lot of the things that I'm showing you here with something called AKS Automatic. And I promise you, this is actually my only slide. So if we go here, I really want to go quickly and show you something, and we can skip just some of these right now. And friends, I want to leave you with this here. It is quite interesting. A lot of us can do this. We have experience doing day-to-day operations with Kubernetes. Now, if you are looking for something that will make your life a little bit easier with AKS, and AKS, it's 100% a validated platform to run AI workloads. They just show you that. AKS Automatic is probably something you should investigate as well. Why? Well, a lot of the defaults from a production standpoint have been taken care of for you. We based on telemetry that we ourselves have from our own experience and customers. We've enabled things like a typical scenario where customers will have a lot of workload. We have enabled a ton of things like Grafana or the proper CNI for that as well. We also make sure that all of the safeguards are built into the cluster. So I would suggest that, once you're looking into this, that also look into Automatic, because I do think there is a lot of value there. All right. With this, I will wrap it up. I can see some stuff in the chat there. Feel free to reach out. I'm happy to answer any questions. And thank you.
Thank you, Diego. Thank you, Anton. And thank you, everyone who joined us today for today's session. I think it was a very insightful one. And like Diego mentioned, please feel free to reach out to Diego, Anton on LinkedIn, and I'm sure they will be able to support you guys with any questions you might have. In the meantime, I do have a QR code right here on the screen. We would appreciate it a lot if you could take some time to scan it. It will take you to a survey, and right there, feel free to give us feedback about today's session. At the end of the day, we strive to create excellent content for all of you, so any comments, any feedback will be appreciated. With that being said, thank you so much, everyone, for joining us today. If you missed any part of today's live stream, you will be able to come back and rewatch it in 24 to 48 hours right here on the Microsoft Reactor YouTube channel. Thank you, everyone. We hope you have a wonderful rest.